I'm going to record this one, and then we'll go ahead and get started. So it looks like it's a lot of standards, but by now you should kind of get an idea of what that means is that none of the standards are especially difficult. And so these are actually all the standards for polymerization. I can't guarantee we'll get through every part of polymerization today. A few of these things will go into next class's lesson, especially topics of amino acids. Amino acids, will be setting those aside and looking at those next class. But today we're going to be looking at both types of polymerization, addition polymerization, which we have seen before, and condensation polymerization, which is new. And so, does anybody remember what is a polymer before we get started? What is a polymer? Well, it is an organic molecule, but it's a specific type. What type? It's a chain of a bunch of repeating molecules, right? Which we call monomers. So it's a very long chain organic molecule that has repeating segments. And we learned last year how to come up with what those repeating segments were, at least for one type of polymers. We learned about addition polymers last year. And so if you'll recall, what we would do is we did this. Where the double bond was, we would write the four sides around it with whatever was there. And to predict the polymerization, we would break the pi bond. We would extend out both ways like this. And then we would know this is connecting to itself over and over again. So we would write two lines hanging out. And then we would write a parentheses and a little n, where n was however many times it repeats, which could be in the thousands, could be in the 10,000s. But this was the idea of turning a monomer into a polymer. So this is a monomer, which is 1 unit. And this is a polymer, which is many units. And so I'm just writing that to give you a reminder of what this was, because it's been a while since we've looked at this. The last time you've looked at this was when you were studying for the AS Chem exam. So I do know it's been a while, but I do remember that this was a topic you were all generally really good at, like in your practice quizzes that you would take and your tests that you would take. I don't think it actually showed up on your paper 2 last year, unfortunately. Did not show up. But you never know. So we're going to start by revisiting this type of polymerization a little bit more, and then we're going to go to a new type of polymerization. Most people are done writing, so we'll go ahead and continue. All right, so in AS Chemistry, like I said, we had learned about this specific type of polymerization where we would put these monomers together. The requirement was that you had a double bond on your small molecule, and it was around that double bond where you would break the pi bond, extend out, and write your dangling covalent bonds. These are called dangling bonds. You may want to write that because you're going to need dangling bonds for both types of polymerization, meaning that it's just extended out over and over and over again. It's kind of the same thing as saying etc. The reaction conditions, you could use heat, pressure, or a catalyst for addition polymerization. So what we're going to do is we're going to take a look back at a paper 2 question, meaning this is from AS Chemistry, but you could be given addition polymerization questions easily as well on a paper 4. They would only be worth probably like 1 mark just because it's something from the past. So usually they're low marks. All right, so it says CHClF2 is also used to produce the monomer tetrafluoroethene. Then you could use this to produce polytetrafluoroethene. State the type of polymerization. It's called addition. That's the first type that we learned. It's called addition, where you add the monomers again and again and again and again. It's always called addition when you have the double bond. And then it says to draw the repeat unit, and it's only worth 1 mark. So to draw the repeat unit, what do we have to start by writing? What should we be looking to write first? This, right? So C double bond C. How many additional groups do each of these carbons get? How many additional bonds do each of these carbons get? 2, right? And we've got a total of 4 fluorines. So there should only be 1, 2, and 1, 2 here. So this is the monomer, but this is not the answer. How do we get the repeat unit? What do? You have to break the pi bond end, extend it both directions. So now you would get the single bond C, still F, still F, still F, still F. But now the new thing that you have to know to do is to extend out those bonds in both directions. You break the double bond and make 2 single bonds. And what else to get the repeat unit correct? Parentheses around the dangling bonds, and then a little N. So let's take a look at how this looks instead of on a paper 2, on a paper 4. So the next question has this on a paper 4. It says addition polymers can be classified into 2 types. They're telling you, which means that you may not have ever heard this before. So sometimes you'll be told on a paper 4 information that you then need to use. It says you could have a homopolymer, which is a polymer like we've seen, made up of the same repeating monomer over and over again, or something called a copolymer. So you want to underline that copolymer. A polymer made up of 2 or more different monomer units. And then it says the reaction of propene with phenylethyne gives a copolymer. Draw a length of this chain that contains 1 molecule of each. And notice how they bolded each. That means underline it for yourself. That means it's a key that they're giving you, that this is really important that you do this. So this one's worth 2 marks instead of 1 mark. Where should we begin? Where did we begin last time with the easier question? We wrote around the double bond. So we're going to do that both for propene and for phenylethyne. So I'm going to write propene first. C double bond C. What would be on this first carbon for propene, the one on the left? What would the 2 things connecting to that carbon be? An H and a CH3. It doesn't matter what you write on top and what you write on bottom. Just one is at the top and one is at the bottom. And then on the other side, the other carbon that we care about has what connected to it? H. And what are we connecting this to? So we want to show that we are connecting this to something. What is the other thing we're combining this with? Phenylethyne, which you haven't learned how to name, but that is a benzene. Phenyl is a benzene that's going to come up in Unit 6. You don't have to write out the benzene here. You just have to write out the different groups. So these are the 2 carbons. So C double bond C. What are the 2 things connected to the carbon on the left? H and the whole thing here, C6H5. If you knew it was benzene, you could draw it out, but you don't have to. You can write it exactly the way it's provided to you. And then on the other side, it's just HN, H. So the question is, how do we combine these into a polymer? We need to extend this out, right? And extend this out. We need to extend this out and extend this out. But these 2 will connect to each other. Does that make sense? So I'm going to rewrite them out again. This time, instead of with double bonds, I'm going to write them with single bonds. And then I'm going to write the other one. And then what I'm going to do is I'm changing the color as I draw my new connections. So these 2 that are linking together, I'm going to write this new bond here that links the 2 monomers together. And then on the outside, we should still have a dangling line and a dangling line. And then how do we wrap it up? And so this satisfies the requirement because there's one molecule of each of them. And then this is the repeat unit. See if that makes sense. So this is once again how addition polymerization could look on a paper 4. The next question, we go backwards, meaning they give you the polymer and they want you to sift out what are the monomers from it. So I'm pausing because I see most people are done writing. Did you finish? Yes. Did you finish? Let's try the next one. All right, so this one, they've given you a copolymer, a different copolymer, the same. And it says, draw the structure of the two, so underline that word two, the bolded word is important. Two monomers which make this copolymer. Copolymer means the two monomers are different from each other. So can you pick out the repeating pattern here? It says, this first carbon has a CH3 and a Cl. The second carbon has CHH. The third carbon has C2H5 and H. The fourth carbon has CH3 and H. Can you pick out the pattern? You see where a repeat starts. I'd say that there's a repeat here into here. You see it? Because it's a section of the chain. So I would say that this is a unit. This is that same unit. And this must be the other one, the one right here. So now they're asking you to go backwards, meaning you have the polymer, go back and recreate the double bond. So let's take a look at how to do that. That color again. This would be my first one, CCHH, Cl, CH3. And instead of the two dangling lines, what do? Put the double bond back, right? Put this back in. And then for the other different one, because these two are the same, the one in the middle is different. We'll do C, C, C2H5, H, H, and CH3, and the double bond goes back in the middle. One mark for each correct monomer. This concept is ringing a bell? All right, so that was the review. And this was a topic that shows back up in A level, but was something technically from AS. You'll also notice when you took the practice paper 4 last week, there were a couple AS questions in there. There are always some AS questions in there. Some you may be more familiar with, some that are those random questions. I believe the one they put was, what is the catalyst for the Haber cycle? For the Haber equation, which was the nitrogen plus hydrogen makes NH3, that was iron. You knew that back in AS chemistry because it was one of the AS chemistry standards. But if you said iron, you got it correct. All right, so second type of polymerization is called condensation. So we've heard this term condensation before in organic chemistry. And before organic chemistry, we heard condensation back in early science classes. What does condensation mean? When I think of condensation, what do I think of?
Gas to liquid.
Gas to liquid, which means water, right? So when we think of condensation, we think of water droplets on a soda can. That's what I usually think of when I think of condensation. So in a condensation reaction, what you're doing is you're taking out water. That's the key. Every condensation reaction takes out water or another small molecule. So it's either going to be taking out water, or there's another one that I remembered last night as I was rewriting this. HCl can also be taken out in a condensation reaction. And I'll give you the requirements of what you need for each. So in order for a condensation polymerization to happen, the molecules have to have specific functional groups where you can either take out water or you can take out HCl. And those specific functional groups include carboxylic acids, amines, and this is actually, if you study bio, you've seen this reaction before. Because if you take out water between two amino acids, you'll get something called a dipeptide, where this right here is called the peptide bond. And that's what we're going to be going over next class when we look specifically at the process for amino acids. But condensation in its outset is just taking out water. OH from the carbonyl group and H from the amine or the alcohol. And we'll see more of that in just a little bit. So this tells you how condensation happens. You can either have those functional groups on the same molecule and have the same molecule repeating over and over again, or you could have on two different monomers. And notice at the bottom it says condensation polymerization leads to the formation of small molecules as well, which is why I said you're either going to take out water in these questions or HCl. And I'll show you when it's HCl instead of water. And so what I did was I added this slide. I think hopefully it makes it a little bit more clear. You could write this in your notes if you're writing notes down on paper. The requirements for condensation polymerization versus addition. If you have addition polymerization, the requirement is that you must have a double bond. No double bond, no addition polymer. And that's what we had been looking at back in AS. Condensation polymer, you must have either OH or NH on one of the monomers, meaning an alcohol or a amine, right? This is an alcohol, and this is an amine. And then on the other monomer, you must have a carboxylic acid. For this new group we're going to learn about in a little bit called an acyl chloride. You can go ahead and write it down now just because it's coming. COCl. And so the idea is that you've got the alcohol or the amine on one organic molecule, and you've got the carboxylic acid or the COCl on the other. In the alcohol and the amine, the hydrogen is going to get pulled off. So for the alcohol, which is OH, and amine, in both of these cases, you're taking out just the hydrogen. So that gives you the H part of water. And then for the carboxylic acid, and acyl chloride. And you're going to want to write this down because this will be very important as you make decisions. If you understand this, it actually makes the work we do pretty easy. In the carboxylic acid, we remove OH. In the acyl chloride, we just remove Cl. So circle that, or put a box around that, because that tells you exactly what you're going to remove from each of these different functional groups as you are making condensation polymers. Remember, H and OH together make water. H and Cl together make HCl, which is hydrochloric acid, either in its aqueous form or gaseous form. So if you understand this and how this works, this is almost all of those standards, literally just within this one slide. And it's just looking at different scenarios from here, where you have different combinations of these groups. One of this type and one of this type. All right. Quick picture. So this is actually a slide that I believe I gave you last year, if I recall. When we did something called esterification, which is making an ester, we actually went over this process where you would take away the OH from the carboxylic group, you would take away the H from the alcohol, and when you combine an alcohol with a carboxylic acid, because you removed the water, you connected these two segments, and you would get an ester as a result. which you do need to remember your functional groups. And ester is when you have COOC. I might put an additional practice set for you to do functional groups beyond the regular homework, just because you need to go over them. They're super important that you know the differences in your different functional groups. So if I have an alcohol and a carboxylic acid and I combine them together, I get an ester, and the other molecule is water. In condensation, you always eliminate a small molecule. Typically water, but could also be HCl. These are some options of what you could be combining. You don't have to memorize them. You just have to memorize the requirements that I had told you before. But this is a scenario where you can use the same monomer against itself, because this has both the carboxylic acid and the alcohol. So you could combine many lactic acids together to make polylactic acid. This is lactic acid is used in your muscles. If you ever have heard of DOMS, those of you who like to lift weights might have heard of DOMS. It's delayed onset muscle something. And what it is lactic acid builds up, and you need it to build up, and it hurts because acid generally hurts. But it gives you that burn. And you know when you get that burn that you're actually building muscle when you're lifting weights. This is the molecule that does that for you. It's called lactic acid. It can be made into a polymer because of the OH group on the carboxylic and the H on the alcohol. These are a couple of acids and alcohols where you would have the carboxylic acid on one molecule and the alcohol on the other, and you would combine these together to form the polymer between the two. So you're always going to be looking to identify the H on the alcohol or the amine and the OH on the carboxylic acid to know what you're going to take out and then link the rest together. And that's what we're about to be practicing. Right. Yeah, and that's actually the way it is in bio too. When you do dehydration synthesis, the OH should be coming from the carboxylic group always. It's a topic that copies between both classes. Continue. All right, so first type of question, this is from the textbook. However, I have seen questions like this on a paper 4, and you'll see that in the next slide. So this one comes from the textbook. Which of these monomers form addition polymers and which one is condensation? Take a look at the first one. Do you think that would be best going addition polymerization or condensation polymerization? What does it have the requirements to do? Condensation. Because the H is going to come from the amine and the OH is going to come from the carboxylic group. So this is condensation because you can remove water. The second one, got a double bond, it's got to be addition. The third one, condensation, looks very similar to the first one. And the last one, also condensation. Now, presented to you on a paper 4 on the next slide. How would this look coming from Cambridge? Assessing the standard coming from Cambridge. Paper 4. Notice it's only 1 mark for all 3. So how easy do they think this question is? You have to get all 3 correct. So the first one, this is your pair. Would it be best classified when I put these monomers together as a condensation polymer or an addition polymer? The first one. Condensation. The second one. Also condensation. Because the H is coming from here and Cl is going from there, and it's HCl is the small molecule. That's why I made that little addendum, that it might not only be water, it could also be other small molecules. Typically it'll be HCl because we work with acyl chlorides. So this is condensation. It's still classified condensation. And then this last one, it's addition. How do you know the double bonds there? They didn't write it.
The H's.
The H's, there's 2 missing on each, right? So they're expecting you to catch that. That even if they don't give you a double bond because this doesn't have the maximum amount of hydrogens, that there is a hidden double bond here. You may want to write it for yourself. CH, H, H. Like if you wouldn't have caught that. If you wouldn't have caught that, Try writing it out. Each of these carbons are missing a bond, like they're missing a bond. So this has to have a double bond to complete it, which means it's an addition polymer. Sneaky, sneaky. But it definitely doesn't have the requirements for condensation, so it would have to be addition. All right, so that's coming from paper 4. This next question is also from paper 4. And so it tells you fumaric acid can form addition and condensation polymers. And we're going to take a look at both types of polymerization here. Draw the repeat unit of the addition polymer first. And then I had to write the little note that's fumaric acid up there. So how would we do the addition polymer? What should we do first? Look for our double bond. So that's here, the C and the C. You want to start by writing out what's around that double bond because you want to create it in the way that it makes sense to you. So I'm going to write C double bond C. On this carbon here, what are the two groups to attach to it? It has to be two groups. One of them is the CO2H, but what's the other one? There's another thing coming out of it. It doesn't have 3 bonds. It has 4. It's a H. Because it's skeletal, they're not writing the other hydrogen. Remember that? So this would be a hydrogen. Yes? And on the other side, I'll have the same thing. A CO2H and a hydrogen. So then how would we write the repeat unit? C single bond C, CO2H, CO2H, H, H. And how do we wrap it up? Dangling bonds, right? These are called the dangling bonds. And around those dangling bonds, you put the little one, like that. The next question is the first one of condensation. So pay careful attention to this next one when we get to it, because I'm going to teach you how to write the condensation polymer correctly. We've done addition many, many times. You know how to write that one correctly, but we have not yet seen how do we write the condensation polymers. How do we write the dangling bonds for condensation polymers? So I'm going to go ahead and teach you that now. This next question says, draw the repeat unit of the polyester. I would underline that word, polyester. Many esters. They're telling you, if you know what's going on, that you got this going on. If you know, you know. Polyester means you've got many ester bonds in this molecule. And they said, when fumaric acid reacts with ethane 1,2-diol, and then it says the ester bond should be shown fully displayed. What that means is they don't care if you do structural format or skeletal format for the rest. But you better show the ester bond. That's this one. So they want to see the COO. This is the ester bond. The bond that links the two monomers together is the ester bond. Yeah. All right, so let's draw fumaric acid again. And so this time, instead of focusing on the double bond, what should I be focusing on instead? The carboxylic acid, right? So I'm going to rewrite fumaric acid, but this time I'm going to write it as C double bond C, and then I really care about showing this. And then I've got this and this. And what am I linking this together with? So this is the fumaric acid from the last slide. With ethane 1,2-diol, right? Ethane 1,2-diol, okay. Could we write that? They didn't give us a formula for that. They just gave us the name. Could we come up with what that is? Ethane means how many carbons? 2, right? Diol means an alcohol on each one of those carbons. Di means 2, right? So you're going to have an alcohol here and alcohol here. What else? Do I have to write all the rest of the hydrogens? You have to include them. Do you have to display them? You have to include them, but you don't have to display them. So if you wanted to write H2, H2, you totally could to save some space. You could do this. You could do that, like that. You could have also done that here, CH and CH. And I probably will in my final answer. All right, so how do we put these two together? They're asking us to draw the repeat unit. What do I need to take out? And so this is where I'm going to use a different color. Where does the H come out of? Where does the OH come out of? This is what you have to remember. The H comes out of the alcohol, and the OH comes out of the COOH. So you have to remove these two things to come up with water. And you have to link the rest together. So how would I link the rest together? What would this become? First of all, the same thing's going to happen to the other carboxylic acid and the other H. So you may want to do something like this for yourself. Those are where your dangling bonds are. Dangling bond. So if we start with the dangling bonds, we would start this at C double bond O. Then what comes next? CH, CH, right? Do we have to write the double bond? You don't have to. And you can condense it. So I'm going to write CH, CH just to show it, but you don't have to. The only thing you must show is the ester bond of them linking together. So I got this and I got this. What comes next? C double bond O. What is that linking to? This is gone, right? This is out. This is out. What is the C double bond O linked to? To the O, right here. So that would make us, I'm going to write that in a different color because this is the ester bond right there. Right, we have to show the new bond, the part that's linking the two parts together. And now for the rest, we would write CH2, CH2, and then what comes next? Typically, they actually don't even write the oxygen here. They'll not show the oxygen at all, and they just show it like this. And what would we put on the outside? Little N. That's it. So one mark for the two correct linked sections with your ester bond showing, and one mark for the dangling bonds with the little N on the outside. So I do want to show, just because it's in the homework. Notice how I didn't for the alcohol show the oxygen. I want to show that here in the homework, this question 4. They are not showing the O on the alcohol side. And they're actually showing, so let me copy the way that they do it. They're actually showing the O on the carboxylic side. So I want to copy how they present it to you. The alcohol side, they don't show the O or the H. On the carboxylic side, they show the CO. This is from the homework just to show how they present this for the repeat unit. This is a different one, but the alcohol side, they don't show it at all. And then the carboxylic side, they have the oxygen. Just to show. The alcohol side, they don't have the OH at all. And the carboxylic side, they have the O showing there. This will be in your homework. All right, so couple other things. And some of this is from the old standards, so it's not necessarily information you have to memorize. It's just helpful information. They used to make you memorize like terylene and Kevlar and a lot of random polyesters and polyamides, and they took that out a bunch of years back. But it's still interesting to be aware that there are some polyesters that have very important applications. Kevlar is one of them. Kevlar is used in bulletproof vests because it's so strong. It's a very strong chain. They use it to resist bullets. And it's resistant to fire as well. So it's used for fireproof, like for firefighters, their outfits can be made partially out of Kevlar. And so fire protective clothing, bulletproof vests, leather worn by motorcycle drivers, all could be Kevlar. This is Kevlar structure. And although you don't need to memorize the structure, what I wanted to point out is what makes it strong is it has an orderly structure with many, something you've learned before called a hydrogen bond. So in the homework you have today, you are going to have a couple questions where you have to answer what type of intermolecular forces there are. Do you remember your types of intermolecular forces? That's why I left this here. Just in case you forgot, because there will be a question in your homework where you have to reconsider this. And remember, AS Chem stuff can show up. What are our types of intermolecular forces that exist between molecules? We've got dispersion, which is also known as ID, and that is utilized for what type of molecules? What are dispersion forces for? The strongest force for? Strongest for nonpolar. What if it's polar? What would the type of force be? Do you remember? Permanent dipole, or PD-PD. Permanent dipole, or PD-PD, if your strongest is polar. So like HCl. Strongest for polar. But what is our third type? Hydrogen bonding. Intermolecular forces will show up here and there throughout this unit and the next one. So hydrogen bonding is when you have H directly connected to fluorine or oxygen or nitrogen, one of the three most electronegative elements, and it's the strongest of the weak forces. Because Kevlar has many hydrogen bonds, thousands of hydrogen bonds, that's what gives it its exceedingly large strength as a material. This is not something that is found naturally. This is something that scientists made in the lab. Some materials are lab made. And I'd say this was made in like the 1930s, if I recall. So we're coming up on 100 years on some of these materials. I'm giving you some time to write this down. Remember that these questions can show up. I do have one in your homework where you have to discuss intermolecular forces with a long chain polymer. So make sure you are writing them down. On the next slide, there's actually another question about addition polymers. There's a lot of addition polymer questions here. So do you need me to go back? You got it? Do you have it or do you need more time to go back? Go back? I'll pause. We're good on time. You may have time to do your homework. We'll see. Because if you look at the rest of the questions, they're all not that, it's not that much. It's just a couple written answer questions. If you want to, you can go ahead and try Shikapnagni while you're waiting. It is an addition polymer question, so you could technically do it. We have done a lot of examples of it. Just you'd have to come up with the structure from the name. So I'll give you some time if you want to get started on it. Why are we? I'm gonna go ahead and move to it now. They're saying give an equation to show, and here it's just talking about rubber. Rubber is an addition polymer. And so it could be derived, natural rubber is 2-methyl-1,3-butadiene, and neoprene gloves are made out of 2-chloro-1,3-butadiene. So if you've ever purchased neoprene gloves, you can buy them at I think it's called Harbor Freight. It's a store where you can buy tools and stuff. They sell gloves like this. You are wearing some 2-chloro-1,3-butadiene. So give an equation to show this polymerization of 2-methyl-1,3-butadiene to form natural rubber. What would we do here? They gave us the name. Do you remember how to go back to the formula? 1,3-butadiene. But means how many? But does not mean 3. But means 4 carbons. So let's start there. And there's 4 carbons in the chain. So start with that. 1, 2, 3, 4. On carbon 1, and carbon 3. So both ends. There is a double bond. What else did we see? On the second carbon, there's a methyl. And what else should we be writing out? All the hydrogens. So I'm going to write hydrogen, hydrogen. No hydrogen here. Hydrogen, hydrogen, hydrogen. Now, it does not matter which double bond you choose to do your polymer around. I'm going to pick here, but you could have chosen the other one. But what you do have to note that for whichever 2 you choose to be your double bond, the other part is just a side group now. And so this becomes, because I'm going to do it this way, CCHH. I know this is a CH3. And then this is CH2. Notice what I just did here. I took this whole thing and I made it a side group. Why is it important that we do it like that? You're not going to be able to show the repeat if you don't know where. Like where to extend the 2 bonds out. So you pick 2 of the carbons that have a double bond, and it doesn't matter which 2 you choose, but whichever 2 you choose, you make the other a side group so that you get this structure, because it makes it much easier to predict what you're going to do than when you look at it like this. You're like, what do I do with this? It's going to make you think you extend out here and here, but that's not what happens, because if you did that, like you'd have all kinds of crazy stuff going on in the middle. You're just going to end up getting confused. So pick one. Okay. So then we're going to extend it out. And we end up with CCCH3, CHCH2, HH, dangling bonds, and an N. The last topic for today is on biodegradable polymers and polymers that conduct electricity. And so this is more informational topics, but that means that if you're asked a question, it's on the informational basis, like some of those ideas. Here we're going to talk about biodegradability. Polyalkenes, addition polymers, are not biodegradable classically. You may remember this from last year. Plastics are not biodegradable because they don't react, because they're just a bunch of hydrocarbons. And hydrocarbons are resistant to chemicals. And what I mean by that is they're resistant to things like acids. You can't take an acid and break a hydrocarbon apart. Hydrocarbons are nonpolar, and they famously do nothing. If you recall, if I have something like this is polyethylene, which is regular plastic. It's completely nonpolar, and it's not reactive. And so it sits in landfills over hundreds of years, and it's a big problem. And so one of the active areas of research that scientists have been working on the past several decades and are still working on now is techniques in making biodegradable plastics, which we do know how to make. We know how to make them well. They still tend to be more expensive. So if you purchase like from Whole Foods or from some of these other places, they'll give you these biodegradable materials, and they can be broken down by microorganisms in the soil, which means by bacteria or fungus. And they do this because they can derive these plastics from plant-based materials that have the bonds that can be broken, which means they are made of condensation polymers. So an important thing to note is that condensation polymers are biodegradable, meaning that you can break up an ester bond, you can break up an amide bond. These bonds can be broken. This can be broken. And it can be broken by acid. And last year we learned how to do that actually. And we'll be going back over it, not today, but next class. Again, this one as well, the CON, this bond can be broken. And so by chemical exposure, you can break down biodegradable plastics. Again, their problem is that they're still on the expensive side in comparison to the production of polyethylene. Photodegradable plastics is another area of active research. Is if you can create groups that, when exposed to UV light, weakens the bond. So if you've got a carbonyl group, the C double bond O, at specific intervals down the length of your chain. So you've got, this just means in between. You've got the C double bond O's. These can be exposed to UV light, causes the bonds to weaken, causes them to break down at the areas of the carbonyl groups. And this, they did include this in the text. There's some debate on whether photodegradable plastics are better for the environment or not because of the fact UV light usually does free radical reactions. And so there's debate on whether or not that's even a great alternative. More research needs to be done on photodegradable plastics. There are also polymers that conduct electricity, like a metal, like graphite. And the requirement for this to happen is something called a conjugated system. Conjugated system is required of pi bonds. And what do I mean by that? Is that a fancy word? Every other carbon has a pi bond. So that's fancy terminology for every other carbon has a double bond. So if you create a polymer where every other carbon has a double bond in that system, we call that a conjugated system. And these electrons can actually flow through because you've got a pi bond and another pi bond and another pi bond. So you've got this thing going on. You've got that thing going on. You've got that thing going on for basic chemistry. I don't know if you remember the top and the bottom for the pi bonding, like the overlap, pi bonds top and bottom. But basically the electrons can flow through those pi bonds as long as it's every other and there's no break in the chain. So we say that these polymers could actually conduct electricity. And benzene, which we will be looking at next unit, is a great starting point for that because benzene is every other bond has electron, has pi electron, same idea. All right, so you will be getting a project shortly on polymers to help you study and go over some of these ideas. And that project you'll be doing that project, you're presenting that project. I believe I usually like to do this project in pairs. So that means that there'll be some groups of 2 and one group of 3 because this is an odd numbered student class. So just so you're aware, that project I'll probably be releasing next week. So for those who aren't going on the Frost Science field trip next Friday, you'll have something to work on.
Just go.
Well, the Frost Science field trip's a different one. That's the one for that's already been signed up for. I'm getting those field trip forms very shortly. All right, so a couple of last questions, and then, like I said, I think you will have time today to actually work on your homework. It's going to be due by Thursday night, but if you can try to get it done now, that's the best way to do things, is to get it done as soon as you've learned about the topic and while I'm here to answer your questions. There's also tutoring today, but not Thursday. No tutoring Thursday because there's a faculty meeting after school. All right, addition polymers are long-term pollutants. Plastics are long-term pollutants, but condensation polymers are often biodegradable. What type of reaction occurs when condensation polymers biodegrade? So when you take this and you break it apart, I didn't present it in today's lesson, it's in next class's lesson, but if I break this apart, you would go back to having the carboxylic acid and, for example, the alcohol. Does anybody remember what this is called? You would have to put in water to break this molecule apart. Does anybody remember what that's called? Putting in water to break a molecule apart. Yes. Close. It does start with hydro. It was one of the types of reactions. I thought I heard it. Hydrolysis. It's called hydrolysis. I think, David, you learned that too, no? Hydrolysis in biology. When you take an ester, you take an amide, and you break it apart by putting in water. You take any large molecule, you break it apart by putting in water. That is called hydrolysis. We're going to go over that next class, actually, how to break the esters and the amides back apart. I just felt like this was enough for today. Identify two functional groups that could undergo this type of reaction. I have one of them right here. What was this functional group again? COOC, ester. And the other one is called amide. Ester is the COOC and amide is the CON, which we'll be talking about later on in this unit more next class. But amide is the CON and the ester is the COOC. Those are the two. You actually get 1 mark for each of them. And then the last slide for today. This is throwing away articles made from polymers after use is a major environmental concern for 2 reasons. Identify each of these reasons and suggest a strategy that has been adopted to try to overcome each of these. So why is throwing away plastic a problem? Give a reason.
Not biodegradable.
Not biodegradable is one of them. Okay. What would be a second one? Yes, that's classic. Yes. Technically a little bit more detailed. What type of pollution? Besides not biodegradable. Do you remember when you burn them, they produce a toxic gas? So that could be an answer. When burned, they produce toxic gases. And they gave a third option. If you got it, they derive from crude oil, and that's a problem. So that environmentally is a problem that you're using a bunch of oil for these reactions to make these. All right, so not biodegradable. What would be a strategy to overcome not biodegradable? Don't think too hard. What's a strategy that could be used?
Instead, use some that
For not biodegradable. Use something that's biodegradable. Use a biodegradable material instead. Use biodegradable polymers instead. So that's a strategy that has been implemented. And for the second problem, which is when they're burned, they produce a toxic gas. What would be, and I heard someone already say it, instead of burning them, what could you do with them? Recycling. So the second solution is recycle. Instead of burn. That's it. That's all. As I said, you don't have to think too hard. If you look environmentally, you probably knew these answers. All right. So 2 things. First, I'm going to give you your work for the day. And then in about 15 minutes, I'll give you back your test. There you go. So you've got time to do this now. It is a rare day where you have time in class to work on the assignment, but we are out of math for what it's worth. So we may go through the lessons a bit faster. Math always takes the longest. Yeah, you can scan show and tell. There you go. Okay.
It says 20.
Radical substitution.
That's the date that she.
With the UV light.
Yeah, that's the she made it.
Oh, they're about to learn that in AS in about, I don't know, 2 weeks probably. Very exciting.